So I'm going to do an example of a series RLC circuit. So the circuit that we're going to do here is going to be power supply, AC power supply, a resistor. Well, let's put a capacitor in here. Let's put an inductor in here. And I'm going to say that the power supply here has a frequency of 450 hertz, and the voltage is going to be 3.25 volts RMS value. Okay, and the resistance is going to be 47 ohms, and the capacitance here is going to be 5.44 microfarads, and the inductance is going to be 17.3 millihenries. And so I have several questions I want to ask about the circuit. So the first thing I want to know is, what is the current in this circuit, and how is the current phase shifted from the voltage? So to do that, we need to know some other things. We know that Ohm's law for AC circuits, V equals IZ. So I is going to be V over Z. We also know that the phase angle is the inverse tangent of XL minus XC over R. Well, in fact, Z is the square root, the impedance is the square root of R squared plus XL minus XC squared. So we need to find the reactances. We need to find the inductive and the capacitive reactances. So the inductive reactance is going to be 2 pi f times L. So in this case, it would be 2 times pi times 450 hertz, and the L was 17.3 millihenries, so that's 0.0173 henries. And so XL comes out to be equal to 48.9 ohms. So what about XC? That's 1 over 2 pi FC. So that's 1 divided by 2 pi times 450 hertz times C was 5.44 microfarads. So 5.44 times 10 to the minus 6 farads. And so XC comes out to be 65.0 ohms. So that allows us to find the impedance. That's R squared plus XL minus XC squared, all under the square root. So that's going to be the square root of 47 ohms squared plus XL, which was 48.9 ohms, minus 65.0 ohms squared. And really, the order you do the subtraction doesn't matter because you're squaring it. But this comes out to be 49.7 ohms. And so that's the impedance. All right, so now I want to know what is the current. So the current is going to be V over Z. So the current will be 3.25 volts RMS divided by the 49.7 ohms. So the current comes out to be 0.0654 amps RMS, or you could write that as 65.4 milliamps RMS. Okay, so either one is an appropriate way of expressing this. So now we have the current, okay, and now we want to know the phase between the current and the voltage. Well, that's real simple. We just have a formula for that. So that's XL minus XC divided by R. So the phase angle is going to be equal to XL was 48.9 ohms minus 65 ohms divided by 47 ohms. So the phase angle is a minus 18.9 degrees. So what does that mean? That means the current is leading. So that means if you made a graph here and you graph the current, okay, and then you graph the voltage, then the current is going to be ahead of the voltage. So this is your voltage right there, and this is the current. So the current is leading the voltage here. All right, so, and we also knew that that had to be the case. Well, how did I know that was the case? Well, I knew that XL was 48.9 ohms and XC was 65 ohms. Notice the XC is bigger. That means that this circuit is more capacitive than it is inductive. Okay, so the circuit is more capacitive than inductive. And so that would indicate that the current leads, because the current leads in a capacitor. Okay. Well, what about power and voltage? Because that's another interesting thing here. So I want to know what's the power dissipated in the resistor. Now, the capacitor, we know we've got the power supply here, got the resistor, got the capacitor, got the inductor. The capacitor and the inductor don't actually dissipate power. All the power is dissipated in the resistor. All the capacitor and the inductor do is store energy in their fields, in the electric or magnetic fields. They don't actually dissipate it. And so all power is dissipated as heat in the resistor. So that should be I squared R. And so this is going to be I RMS value here. Okay, so that would be equal to 0.0654 amps RMS squared times the 47 ohms. And that comes out to be equal to 0.201 watts. So that's the power that's being dissipated. Now, what's the power supplied? Now, in DC circuits, power supplied is I times V. And so you might naively think this would be 0.0654 amps times 3.25 volts RMS, and that would give you 0.213 watts. Well, that's wrong. You know it's wrong because those numbers don't match. Okay, so they have to match. The power supply has to be the power dissipated. Well, if you remember from our lecture here on the power factor, then really because the voltage and current are out of phase, you need to know the component of the current that is parallel to the voltage, or the component of the voltage parallel to the current. Either way, same thing. So that gives you IV cosine theta. So the power is going to be 0.0654 amps, 654 amps, times 3.25 volts times the cosine of 18.9 degrees. Again, it's cosine, so it doesn't matter if it's plus or minus. And so if you do that, what you come up with is 0.201 amps. And that actually matches the power that is dissipated. So that sounds like it's working just fine. Well, for our circuit here, if I take a voltmeter and I put the voltmeter across here, the voltmeter will read 3.25 volts. Now this is be like an analog meter that's measuring the RMS value. Okay, so it'll read that. Now, if I put the voltmeter across here, the voltmeter, the analog meter is going to read the RMS value here. So the RMS voltage here is going to be equal to I times R. That's VR. So if you multiply that out, then what you get is 3.07 volts. Well, that does not add up to 3.25. Well, yeah, because you're used to putting your voltmeter there and there. Now, if you do put the voltmeter there and there, you get 3.25 volts. Well, so you put your voltmeter here and see what happens. Well, the voltmeter there, VC, is going to be I times XC. If you multiply that out, that's going to be 4.25 volts. Oh, wait. That's more than the original voltage. How does that happen? Well, let's put the voltmeter right here. So we put the voltmeter right there. VL is IXL. Voltmeter there, if you multiply that out, it's 3.2 volts. Well, wait a minute. We're used to having the voltmeter, we're used to thinking the voltmeter there to there is the sum of all of those. So we would expect the total voltage to be VR plus VC plus VL. So why is it not the case? Because clearly those don't all add up to 3.25. What's going on here? Think back to scalars and think back to the, not just scalars, but think back to, the phasors. If you look at the phasor diagram, remember that the voltage on the resistor is in sync with the current, but the voltage on the capacitor and the voltage on the inductor are out of phase with the current. So that means these voltages are those voltages not at the same time that this is that voltage. So that means you cannot just add because they're out of phase in time. So because they're perpendicular, do is you say that the voltage is going to be the square root of voltage R squared plus the voltage L minus voltage C. Remember, they're opposite directions, so you take the difference there. If you do that and figure this out, that would be square root of 3.07 volts squared plus 3.20 volts minus 4.25 volts squared, and that comes out to be 3.24 volts. That RMS. Now that is within rounding error of what we know it's supposed to be, which is 3.25 volts RMS. So that means you have to add it in this fashion. Now, this circuit is not at its ideal. So the next question is, what will we have to do to change the frequency to make this a perfect transmittable circuit? In other words, as best as it can be, because right now the inductor and capacitor are fighting here. So I want to have the maximum current flow. Now there's an easy way and a hard way to find maximum current flow. I tend to be lazy, so I like to do it the easy way. I know that for this circuit, it's going to be, we know that V equals, we know that the I equals V over Z. We know that Z is square root of R squared plus XL minus XC squared. So when XL equals XC, then that means Z is just equal to R. At all other times, it's bigger than that. So that's going to be the minimum value right there. So we need resonance. So the resonance for this circuit, what is the resonance for the circuit? When XL equals XC, then that gives us the resonant. And so the resonant frequency, XL 2 pi FL equals 1 over 2 pi FC, or in other words, algebra, the resonant frequency is going to be 1 over 2 pi square root LC. So if you plug in the numbers, that comes out to be 519 hertz. And so what would be the maximum here? The maximum current would just be V over R. So that would be 0.0691 amps RMS. So that would be your ideal for this particular circuit. Anything else, and you're not at the resonant frequency, and so it's going to be less than ideal. At 0 hertz, you get no current, and then at super high frequencies, you get no current because of the inductor and capacitor fighting you.